right. Our next speaker this afternoon is Doan, and she's joining us here this summer from Pomona College. Has been working this summer with Nick and Jason, and today she's going to tell us about her project building a telescope simulator for testing the Henrietta spectrograph.
Thank you, Wen, for the introduction. I'm super excited to be here and tell you about my work. So this summer, I designed and built a telescope simulator for testing Henrietta. And for those of you who don't know, Henrietta is a spectrograph that studies exoplanet atmospheres. So the first question that I want to address is, how do we probe exoplanet atmospheres? And we do this by using a technique called transmission spectroscopy. So let's say that you have an exoplanet orbiting a star, edge-on, and as the planet makes a transit or passes in front of the star, part of the starlight is going to be blocked by not only the planet bulk, but also by the planet's atmosphere, resulting in a transit depth. And if you observe this exoplanet transit depth in different wavelengths, like over here, you're going to have a transit depth curve, which shows the changing transit depth with respect to wavelength. So because the atoms and molecules present in an exoplanet atmosphere are going to have transitions at very specific wavelengths, these are going to influence the amount, like the depth of the transit that you get at those specific wavelengths. So that is why using a transit depth curve, we're able to extract information about the chemical composition of an exoplanet atmosphere. Now, one challenge with observing exoplanet atmospheres is that these observations require a very high level of spectrophotometric precision, or in other words, a very low level of noise. So these two figures also show like transit depth curves, but we're comparing the high noise scenario with a low noise scenario. And as you can see clearly, in the low noise scenario, we're able to detect signals at a much higher confidence level. So at Carnegie, we're building an instrument called Henrietta, and this is a spectrograph that observes exoplanet atmospheres with a very high precision level, down to 50 parts per million. Henrietta covers a near-infrared wavelength range from 0.6 to 2.4 microns, and it's gonna be commissioned on the 1 meter scope telescope in Chile. So this plot over here shows the expected target coverage of Henrietta. And the plots here are the targets. And we're showing the distribution in terms of estimated transit signal in parts per million and J-band magnitude, or how bright a target is in the near infrared. So the key takeaway from this graph is that if you go up along the y-axis to get to brighter targets, that is the region where Henrietta is predicted to achieve a 1 sigma noise level of 50 parts per million per spectral resolution element. And so this is really remarkable. And so there are a lot of sources of noise that may contribute to Henrietta not achieving the spectrophotometric precision level. And image quality is a dominant source of noise. So we want to make sure that Henrietta's optical quality or image quality is not a limiting factor here. So that is why we are building a telescope simulator to test that image quality of Henrietta. So what is a telescope simulator? Essentially, this is a physical laboratory instrument that produces an output signal that's similar to that produced by a telescope. And that output signal is going to be fed into Henrietta to facilitate its testing. So just to illustrate this concept, I'm showing here a diagram of a Cassegrain type reflecting telescope. In this diagram, you have light coming in from a very distant object, such as a star, and it comes in parallel rays and hits the first surface, which is the primary mirror of the telescope. That light is then redirected towards the secondary mirror and then refocused onto the telescope focal plane. There it forms an image of a point source. Similarly, for a telescope simulator, you have two lenses, a collimating lens and a camera lens. The collimating lens takes in light that diverges from a source and makes it parallel, whereas the camera lens refocuses those collimated beams of light onto a detector plane to also form an image of a point source. So during my design process, I used an optical design software called ZMAX Optics Studio, and these are my two designs of the telescope simulator. So they look a little bit fancier than the diagram that I just showed you, but essentially they carry the same idea of a collimating lens and a camera lens over here. So my system, I designed it with the scope telescope's focal ratio and pupil position in mind. My telescope simulator uses off-the-shelf optics that are 1 inch in diameter. And because chromatic aberration was a dominant source of aberration in my system, I made sure to use achromatic doublets, such as these ones, to correct for this effect. And a key feature of my telescope simulator is that it produces images that have radius of 13 microns. So this corresponds to about 3/4 of an arcsecond at the SWIP telescope, or slightly better than the best image quality that you can get from the SWIP telescope. And this will really allow us to test the limits of what Henrietta can do. So now you might wonder, why do I have 2 designs here? And the reason for that has to do with the limitations of working with off-the-shelf optics. So the lens materials I work with have rather narrow transmission ranges. So it was difficult to have one design that's optimized for a very broad wavelength range, which Henrietta covers. So to circumvent that problem, I elected to have 2 designs instead. The first one is optimized for 0.621 micron, and the second one is optimized for 1.1 to 1.5 microns. And another thing that I would like to emphasize is that there are a couple of things that I optimized for when I designed my system, and those are root mean square spot sizes, which measure the spread of light rays in the image plane, as well as camera focal ratio and system compactness. And because of those prioritizations, I had to make a few trade-offs in terms of magnification and pupil matching. But fortunately, as it turns out, these trade-offs don't really make much of a difference in my system's performance. So the next question is, how am I mounting this telescope simulator? So this is a mechanical cartoon showing the assembly of my system. The lenses that you just saw all go into this lens tube, which is this yellow rectangle. The lens tube is held together by 2 cages that are mounted on the optical table via 2 pillar posts. And to the left of the telescope simulator, there's a fiber-coupled light source, and light from the source passes through a diffuser to make it very uniform, which is in this lens tube over here. And finally, it enters the pinhole, and there it enters the telescope simulator. So that is the cartoon, and here's the actual assembly that I just completed yesterday. Yeah. So in terms of progress, this summer I worked on the optical design and the assembly of my telescope simulator, and I'm currently in the process of tolerancing and testing my system. And in the fall, when Henrietta is complete, my telescope simulator is going to be used for testing the image quality of Henrietta, as I mentioned before. So this image on the right, this is a photo of showing how I'm tolerancing my system. So this is a photo of a machine called Optocentric, and I'm using Optocentric to measure the lens manufacturing defects as well as the alignment errors present in my system. And then I have to figure out how to compensate for these errors and defects in order to make sure that the image quality of my telescope simulator doesn't degrade too much. And yesterday, I also acquired preliminary results for my short wavelength channel from 0.621 microns, which I just want to show it here. So we start with a pinhole object, which is the image on the left here, that has a light profile that is perfectly sharp at the edges. But then we expect that the telescope simulator is going to output an image that's first demagnified. So it has a smaller radius, but also its edge is going to be smeared out a little bit, and that is the result of aberration coupled with like the imperfections of the optics. And then this is what I measured with a microscope objective. And so as you can see, it's pretty consistent with what we predict. It is demagnified to a similar degree as my simulated image predicts. And it's also smeared out in the similar fashion compared to my simulated image. Oh, and another thing that I would like to mention, I measured the pixel size of this microscope objective, and turns out each pixel has a linear size of 600 nanometers, which is 1 wavelength of light. So this is pretty cool. So in conclusion, I would like to drive the following points home. Henrietta is a new exoplanet atmosphere spectrograph that is designed to perform spectrophotometry of exoplanet atmospheres in the near infrared down to the precision level of 50 parts per million. And we want to confirm that image quality, the image quality that Henrietta delivers does not become the limiting factor to achieving this spectrophotometric precision level. So that is why we designed and built a telescope simulator. Our telescope simulator is optimized for 2 wavelength regimes separately, and it also produces images that correspond to 3/4 of an arcsecond at the SWIP telescope, or slightly better than the best image quality that you can get from the SWIP telescope. And finally, we are in the process of tolerancing and testing our telescope simulator. So that concludes my presentation, and thank you so much for listening.
Can you go back to your test results? I have to ask, why is there that little bit of asymmetry in your test image?
So this is just like a preliminary result, and haven't analyzed this image carefully, but so I think the asymmetry, like the slight asymmetry that you see in this image over here, might be indicative of like some tilt of like the surfaces in my lens system. Yeah, or like the result of some kind of aberration that I did not know about, that results from like the manufacturing defects, something like that.
Okay, thank you.
Other questions?
Thank you, New. Fantastic presentation. I love the way that you talked about exoplanet transits. Like, what a great introduction. I was curious about the achromatic doublets that you mentioned. I don't know if you could briefly go over how they can limit chromatic aberration, or if that's in a little bit too much detail for at the talk like this.
So chromatic aberration is basically this this phenomenon when you have light of different wavelengths being refracted by a material differently, and so they're gonna converge or like focus at different points. So if you have just like one lens material, like one glass piece, you're gonna see this chromatic aberration effect. But then if you have like so this achromatic, let me see if I can. So for example, this is an achromatic doublet, and it has 2 pieces made of 2 different glasses, and one has like high dispersion and another one has like lower dispersion. So the negative surface in the achromatic doublet is going to correct for whatever like dispersion that you get from the first one.
Okay, yeah, great. Thank you so much.
Okay, we have a question from Andy McWilliam. He says, nice work, congratulations. Have you measured the spot size in different wavelengths to check on achromicity?
So I have not measured the spot sizes, but it is what I'm planning to do right now in the future. And so in terms of spot sizes, my 2 systems produce root-mean square spot sizes that are less than 13 microns. And those spot sizes, when concatenated with like Henrietta, is going to produce like a total points per function error less than 23%. So that is the prediction for my system, and I'm gonna measure it after this. Yeah.
Awesome. Let's thank me again.